Welcome back to the calculus class. Hopefully you have reviewed the properties of the limit and also the definition of it too, which are more about the theoretical stuff. However, which is also very, very important, which can help you to understand calculus fundamentally, deeply, and also can really help you to resolve many questions as we have already showed previously. So in today's lecture, we're gonna jump into something maybe not that abstract, maybe everybody will more into, which is about the calculation of the limits. All right, let's start. All right, so let's continue about the limit properties. We talked about the uniqueness property last time, and this time we're going to talk about the locally bounded property. So what is it? Well, the definition about this theory is, so if there's a limit, right, for the function f(x), so when x approaches to x0, f(x) approaches to a. So it means there's always exists and positive number n. So when you choose x in this range, from 0 to delta x, which means you're in the neighborhood of x0, right? Neighborhood of x0, and the range is about 0 to delta x. So there's always means the f(x) absolute value is smaller than n, which means the f(x) is also bounded. Okay, let's look at this on the function graph here. Now we have this function f(x). Okay, so it means if we have a limit here, like this one is called a. Okay, it's called a. Around at the point x0, so it means if we choose the neighborhood of x0, right, defined by the formula here, okay, this is like x0 minus delta, this is like x0 plus delta. So in this region, now we have the fx in this region. So for example, we can say the f(x) equals to maybe 5 here and 7 here, right? So it means if n equals to 8 or anything which is a little bigger than 7, now we can say f(x) absolute value of it is smaller than 8. So it means, it is correct, because on this point it is 5, on this point is 7, and now on this point is even lower than 5. So we can say that the function's value is also within a certain range. So we can say it is locally bounded. Yeah, locally bounded. Okay, so how can we prove this? We have a function going like this, but we have another function going like this. Of course, so with the x going into this direction, the function value y will all become infinitely large. However, their increasing rate kind of different. So that's why for example, maybe at this point, maybe the ratio will become to 100 to 1, something like that. Close to this one. So, but in some cases, we will have this. So we can now say, the infinite large over infinite large is definitely going to be 0 or going to be infinite large, depending on the the increasing speed. Okay, so this is the first one. All right, so the second one is about the multiplication, right? So usually we'll have this kind of form, which is confusing us. If we have 0 times 0, of course, it will be 0. we have infinity times infinity, it will become infinity. So these two conditions are too simple for us. But what about this one? Does this function increasing quickly, then this function decreasing quickly? So this is the question. So these two are about the division and multiplication. So let's continue. So the third one is about the infinite minus infinite. So this is about the minus operation. So if we have infinite plus infinite, of course, those give us infinite. So this is too simple for us. What about the difference between them? So like this one is increasing quickly, or this one is increasing quickly. So if this one is increasing quickly, so the difference will be not equals to 0. Maybe the difference between them will become larger and larger. So actually we will have infinite. Okay. But if this one is increasing larger, maybe we have the minus infinity. So anyway, so let's look at this. The next situation is exponential form. So in your middle school or high school classes, exponential function is one of the elementary functions. So for example, we have the base like this, infinite. However, we have the exponent like this. Okay, so although this one is infinite large, but this one is going to be very small. So usually if we have this, we can say it equals to 1, right? But what about we put them together? Yeah, so it still depends on which component will increasing larger. So similarly, we have this one too, or this one too. Yeah, so this is the exponential forms for the infinite the indeterminate forms. So we have those 4 categories, and together we have 7 forms. Yeah, we have 7 forms. All right. So please pay attention here that no matter it's for 0, 1, or infinity, right? Of course, what we're talking about here is about the limit. So it just means the function value or the series value is going to be 0, or going to be 1, going to be infinite. It doesn't mean that we're definitely get there. Limit is about getting closer and closer, but we'll never reach that point. Okay, so I think if you are have no trouble with the previous classes, I think these forms will not be troubles in your eyes. All right, so now we have those very common, very important 7 indeterminate forms we want to explore, but what kind of math tools are we going to have for us to help us? Well, that's the question. Let's see. All right, so let's continue about the limit properties. We talked about the uniqueness property last time, and this time we're going to talk about the locally bounded property. So what is it? Well, the definition about this theory is, so if there's a limit, right, for the function f(x), so when x approaches to x0, f(x) approaches to a. So it means there's always exists, a positive number n. So when you choose x in this range, from 0 to delta x, which means you're in the neighborhood of x0, right? Neighborhood of x0, and the range is about 0 to delta x. So there's always means the f(x) absolute value is smaller than n, which means the f(x) is also bounded. Okay, let's look at this on the function graph here. Now we have this function f(x). Okay, so it means if we have a limit here. Like this one is called A, okay? It's called A. Around, at the point x0. So it means if we choose the neighborhood of x0, right? Defined by the formula here, Okay, this is like x0 minus delta. This is like x0 plus delta. So in this region, now we have the fx, in this region. So for example, we can say the fx equals to maybe 5 here and 7 here, right? So it means if n equals to 8 or anything which is a little bigger than 7, now we can say fx absolute value of it is smaller than 8. So it means, yeah, it is correct because, on this point it is 5, on this point is 7, and now on this point it's even lower than 5. So we can say that the function's value is also, within a certain range. So we can say it is locally bounded. Yeah, locally bounded. Okay, so how can we prove this? Fx prime over the gx prime. So which means actually you can use, the derivatives of fx and gx to help us to calculate the limit of fx over gx. So this one is like if we have the two forms, like the two from the 7 indeterminate forms, like the 0 over 0 or infinity over infinity, we can take advantage of the L'Hospital's rule to find out the limit. However, you have to make sure those two conditions are all satisfied. Okay, so, okay. So this sounds a little maybe abstract. So let's look at one example here. Alrighty, remember what we have mentioned. We're talking about the 7 indeterminate forms. So at that time we have the sine x over x. So when x is going to be 0, we have to consider this limit. So we understand for sine x is going to be 0. For x is going to be 0 too. So, but what about the 0 over 0? What is the limit here? Well, let's check. The first condition is, if fx and gx are going to be 0. Yes, of course, this one's going to be 0, this one's going to be 0. So we have the first condition satisfied. Okay, continue to the second one. What about the limit of the derivative x over g derivative, when x is approaching to 0? So we're checking if, this one, sine prime x over sine x, which is equals to cosine x over 1. So when x is going to be 0, of course, from your trigonometry knowledge, we understand that, the cosine x will going to be 1. And on a denominator's position, we have 1 as a constant. So 1 over 1 gives us 1. So we have, confirmed that, yes, the limit for the fx derivative over the gx derivative when x is approaching to 0 really exists. So this one is satisfied too. So now we can say, yes, we can use L'Hospital's rules to help us to find the limit of our, sine x over x, which is actually 1. Yes. But by now, you must have a question. Well, you already find out, the limit of this one. And then you have to decide if the second condition can be satisfied or not. It's kind of, weird. Yes, this is the rule of, of L'Hospital's rule. Yes. So you have to try to calculate if the limit of the limit of this fx prime over gx prime really exist. If they exist, we can use this to help us to find out the limit of the fx over gx. If it doesn't, we cannot use this rule. All right, so in some conditions, you must be thinking, so Laplace rule will fail, right? Yes, it will fail. So we can change our example here, and then you will find it out. So for example, we change it to the limit. So when it's still about x is approaching, this time approaching to infinity large. All right. So this time, let's see. So we have sine x plus x over x. Well, from the observation, we can see that for sine x, so it is a oscillating function. So no matter how big the x is, the function value sine x is between a -1 and 1. Yeah, it's always between those two lines. Yeah. However, for x, it's going to be extremely large when x is approaching to infinity. So this type of limit is the infinity over infinity type of indeterminate form. So can we try the L'Hospital's rule? Okay, let's check the two conditions. The first one is, do the fx and gx have 0 and or the infinity when the x is approaching to a certain point? Yes, of course. On top, we have this infinity. On bottom, we also have infinity. So the first condition is already satisfied. What about the second one? Well, we have to try it. That's what we learned from our last example. So we have to try the limit of the the fx prime, which is the sine x, okay, plus x prime, okay, over the x prime when the x is approaching to infinity. So we can put this derivative operation into each item in the brackets. So we have on top we have cosine x, and then we have constant value 1. On bottom we only have constant value 1. And for limit when x is approaching to infinity. Alrighty. So now you can see that. Okay. So on top, we still have an oscillating function because for cosine x, it's nothing but the reversed version of sine x. So it looks something like this, but still within the two lines, -1 and 1. So for example, your x is very large, right? So although your x is very large, the cosine x is still oscillating. So for very large value x, maybe you will have maybe 0.5, the minus 0.5. In some cases, when x is very large, you're gonna have 0.9, right? Yeah. So you actually have, numerous values for this, calculation for this formula, cosine x plus 1 minus 1. You have too many choices, infinitely large number of results. So remember, that's why I told you we have to remember, the properties and definitions of our limits. The reason is we have already observed to resolve many complex problems for us efficiently, and also this time it will help us to determine if the limit exists, because we have to check if the second condition can be satisfied. We have to make sure that the limit of fx prime over gx prime do exist. However, for this time, we cannot say the the limit exists just because from the property of limit called uniqueness. It means If we say a limit exists, there is only one number for this limit. However, for this one, cosine x plus 1 over 1, we have too many choices. So this limit actually does not exist. Okay? So it is not satisfying the second condition. So this time we cannot use the L'Hospital's rule to find out the limit for us. But this one, we actually don't have to use the L'Hospital's rule, because for this one, I will write it here. Okay, so when the x is approaching to infinity large, right, sin x plus x over x, it's very easy. Sometimes we're just scared by the form. For sin x, it's a trigonometry function. Its value is oscillating between -1 and 1. So when x is going to be very large, for example, 10 to the power of 9, 1 billion, okay? You can try it. So sin x at most is 1, but x is, 10 to the power of 9, and over the sine of the x, which equals to 10 to the power of 9. So this guy can be ignored, of course. So actually it becomes 1. So we can say the limit of this one actually is 1. So we don't have to apply the L'Hospital's rule to find out the limit of this ratio type of limit. Although it is infinity divided by infinity, which looks kind of complex. However, if you really think it through, using your previous knowledges, like the trigonometry knowledges, understanding, well, sin x is just within a very small range, but x is actually going to be infinity large. Now, it will be very easy for you to find out the limit for this kind of indeterminate form. Alright, so hopefully you have enjoyed today's lecture. So the next one, we're going to continue talking about the limit calculations, about those 7 indeterminate forms using the the tools we're gonna introduce later. Alrighty, so hopefully you can write down what we have talked about today, really understand it by yourself, and get prepared for the next lecture. Okay, good luck, and keep the momentum up. See you next time.